5.6 is going to go a little bit outside the scope of the class, just a little bit here. But I'm going outside of the scope because there's some details that I think the book could have done a better job explaining and making clear. And I think by filling in some of these details, it'll make things a little bit smoother down the road. So before we get into it though, I want to start thinking about that conversation we had when we first started talking about indefinite integrals. I said that these indefinite integrals could actually be thought of as the sum of the area of a bunch of rectangles underneath a curve, right? That's what we're going to be talking about today. But first, we need to go over some notation. We need to go over the sigma notation. Whenever someone writes something like this, what this notation means is you're going to take this function, you're going to put in a. So then you're going to come over and add a plus 1. You're going to keep doing this over and over and over again. A plus 2, dot, 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 plus f b minus 1 plus f of b. So we're going to take and break up all of the numbers from a to b into integer values, right? We're going to say, keep throwing each of those integers from a to b into your function. And add each of those calculations together. That's all this notation here means. So as an example of what we're saying here, let's get a couple basic ones. Let's say we have the sum from I equal to 1 to 3 of I. All we're going to do here is say, plug in 1 for I, plus the next value will be 2, plus 3. And that's it. That's what this notation tells us to do. Just as another quick example, let's say we had 2i minus 1, this thing squared. Then we would plug in 1 for I here, minus 1, that whole thing squared, plus, plug in 2 now, minus 1, that whole thing squared, plus, now we're going to plug in 3. And of course, we can do the calculation and reduce this as much as possible and get an answer, right? Really, the whole point of this notation is just to condense what we're writing. Because honestly, you're going to be doing repeated addition. What's to write that? There's a rule that we can follow and condense our notation using that rule. Why not go ahead and do that, right? So this is a way of condensing notation more than anything else. And because mathematicians are lazy, we love it. So having said that, now coming back to this idea of adding up the area of rectangles underneath the curve to approximate the area underneath the curve. If we take and break the interval from A to B up into even spaces, these are going to be the width of our rectangles. Now, somewhere within each of those intervals, we're going to say, let's choose a point. And the rule that we use to choose that point will have to be the same for each of these rectangles. Now notice, in this example, we've got two different cases, right? We've got an underestimating case and an overestimating case. And the reason why this underestimates is because it's missing a lot of the area under the curve, right? And this overestimates because we're adding a bunch of area outside of the curve, right? So just looking at these two examples, there's a problem, right? The best we're going to do is approximate using this method. Agreed? So having said that, what this method is called the Riemann sum. We have left Riemann sum, right Riemann sums, and a few other different forms here and there. And what they're basically doing is they're taking your x-axis and breaking it up into equal parts. So to give an example, this is going to be a function, f of x. We're going to find the area from A to B. We're going to start by breaking up this interval into a couple of different parts. For the sake of demonstration, let's just break it up into 3 parts. So the length of each of these parts excuse me, I just woke up from a nap. The length of each of these will be delta x, right? Because we're saying they're equal intervals of equal length, I should say. So first question, what is delta x here? Well, in our example, delta x is equal to b minus a over 3. Because we're taking the length, b minus a, and breaking it up into 3 equal parts, right? But in general, if we wanted to add more and more equal lengths, we would say that delta x is equal to b minus a divided by n. So this is if we're breaking up into n equal parts, right? From there, we're going to say, all right, I want the area of rectangles. So I'm going to write some rule about how I'm going to get the height of these rectangles. Already, I made a mistake. I should have drawn it like that. So the height of each of these rectangles is going to be f of a plus, well, in this case, it's f of a. Here it's going to be f of a plus delta, right? Here it's going to be f of a plus 2 delta. So f of a plus delta x, f of a plus 2 delta x. So this is just for example, we're just using this particular rule for right now. we generalize it by just saying f of x star n. This is how we generalize it, just to say, based on however you're going to pick your x values from each of these intervals, you want the nth one every time, right? So n equal to 1, n equal to 2, n equal to 3, so forth and so on. From here, we're going to say, all right, the area of each of these, well, it's going to be f of x star n times delta x, right? That's going to be the area of each rectangle. So just to make that more readable, and now we're going to add each of these up. There should be a n for the area of the nth rectangle. So we would say that the area under our curve approximates the sum from k equal to 1 up to n of f of x k star delta x. So we're adding up the first area up to the nth area, right? So having said that, there's a typo in what I wrote up here. This should be indexed from n equal to 1, or this should be k minus 1. And it's just because of the way the index works. You could write it either way. The problem with this is we have an extra rectangle now. So we have to change the index a little bit. Make sense? So, having said that, I want you all to consider this question for just a second. So, as we take the width of each of these rectangles and send them smaller and smaller and smaller, our approximation is going to get better and better and better, right? What does this sound like to y'all? What are we about to do here? Apply a limit, right? We're talking about sending something someplace. In particular, we're talking about sending delta x to 0. In the past, when we've talked about sending delta x to 0, what happens? It becomes dx, right? So it's starting to look a little bit already like we might be working towards a definite integral, right? So closing out of that really quick. Now delete it. So this is where we're at. The limit definition of the definite integral. Again, a typo. It should be k or n equal to 1 or k minus 1. And while y'all are looking at this, I'm going to step out for just a second.
homework stuff that's outside of scope of the class. I have no idea. I mean, I guess if it helps or whatever. This seems to be more confusing right now.
Did you say anything about the upcoming test at all?
He said it was next week, that's all he said.
Okay.
And he didn't say, like, I'm assuming it's next weekend, but.
Please, no cell phones in class.
Oh, you're good.
All right, so we've got this limit definition now of the definite integral. And what it's telling us is that this integration from a to b of our function with respect to x, it's giving us the area, but it's giving us the area by saying, hey, let's calculate the area of these tiny rectangles and sending their width to 0 and then adding them all up. Make sense? Now, a question might occur to you. Do we have to use rectangles? No, we don't. We don't have to use rectangles. We could use other shapes. In fact, there's a trapezoid approximation as well that gets used for integration. But the basic idea is you're just going to take the area of some nice regular geometry underneath the curve, send the width of that thing to 0, and that will approximate the area underneath the curve. Then when you send that delta x to 0, it comes out to actually be the area. So really, if you want to know the area underneath the curve, you don't necessarily have to do calculus. You can just do the algebra of the summation without the limit. You can approximate it that way. And that's the point of what I'm trying to get to here, is that the way they present what comes next in this book is just all of a sudden approximating this thing. Great. How and why? The reason why is because what we're doing is we're unimposing the limit and saying, yeah, let this thing get as big or small as you want it to. The smaller it is, the better your approximation. The bigger it is, the worse your approximation. So, as a few notes, there's a couple common rules for how to choose your x value that you put into your function. There's the left-hand sum, which just says choose the left side. This is assuming we're indexed using 0 to k minus 1. Excuse me. So there is some arbitrage in all of this. So if we're indexed using my mistake. If we're indexing from 0 to k minus 1, the very first value is going to need to be just a, right? So we're pulling from the left side of each rectangle. The right-hand sum is going to be pulling from the right side of each rectangle. And the midpoint is just going to say take the middle. Make sense? So, how do we use it? Well, we've got a great example here. We've got f of x is equal to negative x squared plus 5. We want to know between x equal to 0 and x equal to 2 what that area is. So we're going to approximate it using 5 rectangles. Now this work is time consuming, so I'm not going to do the entire calculation on the board. What I'm going to do is walk us through these problems. To start off with, we need to break up our interval from 0 to 2 into 5 equal parts, right? So our delta x is going to be b minus a divided by n or k or whatever you want to index it with. Let's say n. Let's say k, just for the sake of keeping what I already wrote on the board. Our a and our b, we already know a was equal to 0, b is equal to 2, k, they said 5 rectangles, so we want to set k equal to 5. So delta x is equal to 2 divided by 5. Now the rule that they're going to use here is the midpoint rule. So xn star is going to be equal to a plus, we're going so far and then choosing the middle, right? So that's going to be like n plus 1 divided by 2, right? Because if we're starting at 0, the middle of this will be 0 plus 2 divided by 2 times delta x plus a, right? Make sense what I mean? So what I'm saying is this is going to come out to be n plus 1 divided by 2 because we're trying to use the midpoint. So we can reduce this a little bit. My mistake, times delta x. Forgot the other part of it. I knew something looked funny. So what we're going to be doing here is going to say, all right, go up to the nth value. We want, well, let's actually write this out. Let's check it. Xn equal to 1, well, 0, 1, 2. Let's choose 2. We should get 5 over 5 here. Just to check our work. X, we said 1, 2, 3. 3 star is equal to a plus 3 plus 1 over 2 times 2 over 5. This is going to come out to be 7 divided by 2. So I've got a typo up here. See what I mean? Because what this should come out to be, it's 5 over 5. Anybody know where the typo is? The typo is the way what this is saying. Here we're just saying we're going to add n many half intervals. Does that make sense what I mean? What we should be doing is saying, okay, go n number of intervals, and then add half an interval. Does that make sense what I mean? So the point here is these are really easy to make mistakes with. We have to be very careful about the way we actually do these calculations. Does that make sense? Folks at home, are you with me? That sounds like a no. So, to explain what's happening, we're going to take the first value, that a, right? Well, let's set n equal to 0. So, what we should get back for this half value is going to be somewhere between a and a plus delta a, right? Make sense what I mean? So since this starts at 0, we're going to have 0 plus, well, n is 0, 0x, plus delta x over 2. So we're just going to be left with delta x over 2. Cool with this? Now, going back to that example of 3, we're going to have 1, 2, 3, and then add a half an interval, right? So this is going to be x 3 star is equal to 0 plus 3 times 2 over 5 plus delta x over 2 plus 2 over 5. Oh, that's why. Okay. This is still doing something wrong. 0, 0 plus. This is doing it wrong. Sorry, guys. Give me just a second here. Oh, that's why. Okay, I miscounted it. We're starting at 0, 1, 2. Should be 2, not 3. That's why I meant to put 2 down here. Okay, now it works. 1/2, 2 over 5. So this is going to come out to be 4 over 5 plus 1 over 5 is equal to 5 over 5, or just 1. First rectangle is n equal to 0. Second rectangle is n equal to 1. Third rectangle is n equal to 2. 5 over 5 is the middle point, and that's what we're using for the height of our rectangle. Make sense? So this checks out. So now, I'm going to put all of this together. We're going to say that the area is approximately equal to the sum from n equal to 0 up to 0, 1, 2, 3, 4. Up to 4 of f of x n star delta x is equal to the sum from n equal to 0 to 4 of f of this whole mess, which I'm not going to actually plug in. I'm just going to leave it like this. So what this is going to come out to be then, once we do these calculations, it's going to be f 1 over x, I mean 1 over 5, that quantity times delta x, plus f of 3 over x, 3 over 5. Damn. times delta x. Now we're going to move to the next rectangle, f of 5/5 times delta x plus f of 7/x, or 7/5 delta x plus f of 9/5 times delta x. From here, we're going to do these calculations. We're going to evaluate f at 1/5, f at 3/5, so forth and so on. Do all the individual terms, or calculate each of the individual terms, then add them up. So what does this look like? What this looks like is to say, breaking your interval up from 0 to 2 to 5 parts. You're going to choose the midpoint of each of those intervals. So 1/5, 3/5, 5/5, so forth and so on. Excuse me. Then you're going to take and calculate your function at each of those midpoints. Then you're going to multiply each of those values by 2/5 and add all of that up. So what they're saying here is, notice you can factor out the 2/5, add up just the function values, then multiply by 2/5 and get your result that way. Make sense? So just to reiterate what the midpoint rule is, you're finding all of your midpoints based on what your intervals are. You're plugging those into your functions, taking the sum of all of that and multiplying by your delta x. Everybody cool with this? As another example, that same problem, negative x squared plus 5 from 0 to 2. As we increase the number of intervals, our approximation gets closer and closer to the real number.
So like, what's the benefit of doing it this way versus like what we've already learned?
So the benefit, it's not going to be immediately obvious, right? Like it doesn't just jump out at us, right? But let's think about all the functions we know how to integrate. There are entire families of functions that mathematicians just can't integrate. We don't have methods for it. And what we do is we apply these sorts of methods. And thanks to computers, we get really good approximations now. So this is really where the point of that is. Like that's really what the benefit is to say that there are some functions you just can't integrate. But we can apply methods like this to get their integration done. Make sense?
Mm-hmm.
And for whatever it's worth, the integral evaluates from 0 to 2, evaluates out to be 7.3 repeating. So, as another example, here we're going to use, again, 5 rectangles. We're going to integrate 1 over x squared plus 1 from 0 to 1. First, can we integrate that? Based on everything we've done in this class, is that an integral we can evaluate? Folks at home, what do y'all think? Based on everything we've done thus far in this class, can we evaluate the following integral? Let me draw it up here on the board. So let's go through our list of methods. First, power rule. That jumps out, right? Can't quite apply it though, can we? What about U sub in the power rule? Doesn't quite apply here either, does it? We could rewrite this as x squared plus 1 to the negative first power dx. Okay, what about the ln now? Not quite. ln in a U sub rule? Not quite. So this is an example of one of those reasons why this is useful. You can't actually evaluate this. Not with the methods we've learned so far in this class. So if this were to show up in a workplace, and it could very well, depending upon what you're doing, anyhow it could, we would have to use one of these methods to approximate the area. Makes sense what I mean? So it's that sort of motivation for why there's just a assload ton of integrals we can't actually solve by hand. So having said that, the way we would go about this, we break our interval from 0 to 1 up into 5 parts, right? Into 5 sub-intervals. So we're going to have 0 to 1 over 5, 1 over 5, 2 over 5, so forth, so on. And then we're going to find the middle value. From there, we're going to say, all right, evaluate our function at that middle value. All right, so each of these would be 1 over 10, 3 over 10, so forth and so on. Evaluate your function at those middle points. Add all of that up, and then multiply by your dx, 1 over 5. Question, does anybody recognize this value? 0.786? It's an important one. Shows up all the time. It's pretty damn close to pi over 2, or pi over 4, I mean. The actual solution is pi over 4. And the reason why is because of trig rules and a bunch of other things that come up. But if you notice, the actual solution is going to be pi over 4. That means we're only off by a decimal. I mean, by 0.001. So 1/10,000th. It's pretty damn close if you consider the scope of these numbers. That's an error that's like 1. That's how big that error is. It's tiny. Or it's on the scale of that, I should say. So it doesn't take a whole bunch of rectangles necessarily to get really good approximations. We only have 5 here. We were already down to 3 decimal points precision. That's huge. So having said that, what about something like this? Again, could we solve this integrand by hand? The method's not immediately obvious to me. So we would approximate it. In this case, we're going to use 10 rectangles in the midpoint rule. So it's going to look something like this, what we're actually functionally doing. Pro tip, something you might notice. On the left side, we're a little overestimating. On the right side, we're a little underestimating. Functions that are always increasing or always decreasing on the interval that you're looking at will have this property. Because of this particular property, the midpoint rule is actually a pretty good approximation in a lot of cases. Because this overestimation is about the same size as this underestimation. That error is really small. Make sense? Looking at the way this breaks down, the midpoint of all 10 subintervals between 1 and 3 are as follows. Or delta x, well, that's 3 minus 1 divided by 10. So that's going to be 1 over 5. Now what's left to do is plug in each of those midpoints into our function, add all of those values together, and then multiply by 1 over 5. And for whatever it's worth, this is what the actual area is. That sucks. And that is horrible to read. There's the way to calculate this is actually there's a couple of different ways to calculate it, and we're going to talk about one of them later on, either today or next class. But if you look, we're only off by, again, small smidgen of a number. So, like I said, I wanted to address this a little bit more in detail because the book finally at the end of all of this tells you, oh yeah, this is the limit of, or you apply the limit to this. This is the limit definition of the definite integral. I think it's easier to think of it forward rather than backwards. So to go through the definition, then see why, but then reiterate, this is what we're doing. Getting better and better approximations with smaller and smaller delta x's, so more and more rectangles. Cool. So here is a great example of an integral we can't actually solve by hand. We can, it takes a trick. But what this is perhaps one of the most important integrals in your life, especially right now. Not just because it's showing up in your class, but because this integral is involved with statistics. And given the pandemic, statistics are a very important issue. This function is everybody's favorite bell curve. So when we start talking about population studies and what percentage of people fall within a certain category, what we're talking about is the integral under this. Which, if you think about it, is actually really amazing. So in this case, we're taking the integral from 0 to 1. Like I said, without using a trick, we can't solve this. So we have to use an approximation method. I hate that they tell us to use the program on page 404 because like, no one's got time for that. But we could go about it and do it by hand, the normal way. We could say, cool, let's break this up into, at first, 3 rectangles. Actually, since I've already got a really small one, okay, close enough. Yeah, these aren't even close to being equal sizes. But what we would do from here is we'd say, all right, find these midpoints. We've got 1, 2, 3, 4 rectangles. So this is going to be at, well, first our intervals, 0 to 1/4, 1/4 to 2/4, 2/4 to 3/4, and finally 3/4 to 1. So our midpoints, 1/8. Here is 3/8. Excuse me, 5/8. 7/8. And our delta x is going to be just 1/4, right? So what we've got here then is a function. This thing is equal to e to the negative x squared. We've got the sum from n equal to 0 to 3, because we're going to, since we're indexing from 0, we have 0, 1, 2, 3. That's 4 in this case, right? So we've got all 4 rectangles here. F of xn star delta x. This thing is going to be 1/4 times f at 1/8 plus f at 3/8 plus da da da. I don't have enough room, so I'm just leaving it at that. Is everybody cool with this? So, having said all of this last weekend, end of last week and last weekend, I had posted a question of the week. And I asked y'all to use a chain rule to figure out a way to integrate a problem that was something like x times x squared minus 2 dx. I said, how might we use a chain rule to integrate this thing? Well, let's think about what the chain rule says. Chain rule, or I mean, product rule, not chain rule. Product rule. Product rule says the derivative of two functions multiplied together, u of x and v of x, this thing happens to come out to be v of x times the derivative of u of x plus u of x times the derivative of v, right? Now let's stop here for just a second. We want to undo this derivative for just a moment. We're going to undo this derivative. U primed v primed dx is equal to the integral of v u primed plus u v prime dx. Everybody agree? I shouldn't really write it like this. I should actually write it as uv prime, because it's the derivative of both of them, right? So undoing that derivative, this is going to come out to be now uv is equal to the integral of v u prime dx plus the integral of u v prime dx, right? Now, there's going to be some trick happening here in just a second. But what we're going to do is we're going to now rearrange these terms. Well, first, I'm going to erase some of this up here. We're going to rewrite these two derivatives in terms of the entire differential form, right? That fractional form. So this is uv is equal to the integral of v du dx plus the integral of u dv dx. Now we're going to rewrite this again as uv equal to the integral of v du plus the integral of u dv. And now I'm going to erase this down here. Get to the awesome, wonderful part about all of this. Here, v isn't a function of u, is it? First thing we need to know is that we can subtract v du from both sides. What this tells us is that if we want to solve particular integrands, we can use what's called the chain rule. Oh, why did I just forget what it's called?
Product rule.
It's the product rule, but for integration, oh, I can't believe I just did that. We're pulling up the book really quick because I need to get examples anyhow. I can't believe I just did that. Talk about an embarrassing moment. Note to self, do not take naps before class. Apparently a bad idea. It is integration by parts. That's the term I'm looking for. Yes. Holy hell, why did that not come to me right away? Okay, that was page 418. We're going to pull up those problems because I don't have anything prepared for them right now. Let's see. Here we are. All right. Let's get it into full screen. It's not going to let me, is it? Yeah, well, if I say function F10, F11. Nope, that was not it. What just happened to everything? Okay. There we go. That's the button I wanted. Sorry about this, guys. Okay, so what we're looking at here is integration by parts. What the integration by parts tells us is that we can break up certain problems that are otherwise unsolvable. Like that problem that I had started off with, the integral of x squared minus 2 dx. Here, we can obviously go ahead and just distribute through, right? But if I had to change this by just a little bit, like this, all of a sudden distributing it won't help you solve it anymore. And that's what integration by parts allows us to address. Are these problems where distribution isn't enough on its own? So as an example, the book uses two functions. Will you not zoom in? The book has these two examples, x squared ex and x ln x. Notice there's no way we can integrate them up to this point. What we have to do is we have to use, again, this idea of integration by parts. If you notice what's happening here, we're really saying we've got these two functions, break them up, and here we've got u, original function, times dv, is equal to uv minus the integral of v du. So it's almost like this dv is doing something like what the chain rule had taught us before. Just like I did a moment ago, we have something like df dx dx. We can think of this as just the integral with respect to f, right? So this dv is really encoding the derivative of v with respect to x times dx. Makes sense what I mean? So here, we've got v, we've got the derivative of u with respect to x dx. Then we have our other two parts. Now, I know I haven't actually explained what we're going to do here, how we're going to use this. But that's because first I want to make note of a couple of these details. So using one of the examples that they provide, let's integrate x ln of x with respect to dx. Okay. Looking at this, we want to break this up into two different parts. We want to break this up into a u and a v. So we could either think of this as u and this as dv, or we could do the opposite, right? Or we could say the ln of x is equal to u and dv is equal to x dx. One of these will be easier to deal with than the other. Any clue which one that is?
The second one.
Yes. Using this, we're going to say what we started off with is the integral of u dv. Now what we're going to do is use this breakdown to get out this form. In this form, we're going to be able to integrate. So if u is equal to the ln of x, well then ln of x just has to stay as it is. If dv is equal to x dx, then v is going to be equal to 1/2 x squared, right? Plus a constant, but we can ignore that for right now. And u so because dv is equal to x dx, v must be equal to 1/2 x squared. And because u is equal to the ln of x, du must be equal to 1/x times dx. Make sense? So now we're going to plug in the rest of this. What we got is going to be the integral of v with respect to du. The integral of v is 1/2 x squared with respect to 1/x dx. Right? So what's happening here? This was our u. This is our v. This is our v. And this is our du. Now notice this second integral, this you can't solve. It's just 1/2 times x, right? So what was an impossible integral that we started off with, this thing is now equal to the ln of x times 1/2 x squared minus the integral of 1/2 x dx. So what integration by parts does for us is it lets us tear the machinery apart and say, nobody report this. Fuck you, you're an ugly ass problem. Let me rewrite you into something I can solve. Cool? People at home, what do you think? Is anybody here?
Yeah.
Awesome, all right. So what do y'all think of this? Does this make sense? Does this jive with y'all?
Well, it's a bit confusing.
It is confusing. And this is going to take a second to really tear apart and understand. This is the second one. So just so everybody knows, there is one more exam. It is next week, and then the week after we have finals. What I am going to do is make myself available to y'all during finals week. The final will be on Blackboard. It'll be done just the same way as before, but I'm gonna make myself available to y'all all week, and you're gonna be able to do the exam whenever you want all week. Otherwise, all the normal rules apply. You're going to have longer to take this exam. I believe traditionally finals are supposed to be 2.5 hours long. You gotta check that. So I don't know the exact time length yet on the final, but I'll let y'all know when I do find out. And again, you'll have all week to take the final, but I'll also make myself available to y'all all week to study or review or go over whatever you feel like you need to go over before you actually sit down and take it.
How many questions did you say the final's gonna be?
So the final is traditionally twice as long as a normal exam, traditionally. And this is why I don't know for sure that my 3-hour mark is right in my head. I think it is. But that seems, that's 3 times longer, not 2 times. And that's why I'm not sure about it, right? But the exam should be approximately twice as long as a normal exam. If you look at your previous exam questions, your previous homework and the review sections, they're all going to be a pretty decent example of what your exam's gonna look like. Excuse me. That said, I do plan on putting together a study guide tonight or tomorrow to help everybody prepare for the final. Any questions about any of that? No?
Will there be a homework assignment after this week's homework assignment?
Yes.
Or-
There is one more homework assignment that will be posted tonight, and it will be due Wednesday.
Next week.
Yes. I know, that's a lot really fast. I apologize about that. If we had actually had spring break, all of this would have been spread out a little bit better. That lack of spring break made the exams feel like it was boom, 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 really fast. So I do apologize about that to everyone. That said, again, are there any other questions? You should make next week's question of the week. How many times do I say that said? I feel like I say that a lot. Anyhow, y'all are free to go. I'll stick around if you have any questions.